Okay, it looks like the technical problems have been solved, so we'll get going with the session now. Thank you everyone for joining and your patience. Okay, so just a very quick overview. Rubin and Euclid are two both complementary and contemporaneous. Actually, can we close this? Excuse me. They're two both complementary and contemporaneous imaging surveys that will produce imaging data sets. From the Rubin side, that's deep optical multiband, whereas from the Euclid side, we have high resolution near infrared. They both have very similar timeframes, 2023 to 29, 2024 to 2034. So they are ripe for exploiting the synergies between the two. Okay, so I think everyone knows I've really put these in the slides just for a reference for people to go back and look at them. Everyone knows what Rubin Observatory is. So this is a picture currently being constructed on the summit. We have a 3.2 gigapixel camera with a telescope with an 8.4 meter primary mirror, 6 filters in optical near infrared. This gives us a very wide field of view, 9.4 square degrees, and hence a very high étendue. And this is what allows LSST to survey the sky very rapidly, to cover the whole southern sky in 3 nights in multiple bands. There are 4 key science drivers around LSST. One of them, which overlaps with those of Euclid, is probing dark matter and dark energy. But Rubin isn't just designed around dark matter and dark energy. We also have a strong program around Milky Way, exploring the transient and optical sky, as well as taking an inventory of the solar system. This shows you here the current survey, the baseline that has recently been released by the Survey Cadence Optimization Committee. During the 10 years of operation, LSST will, Rubin will execute LSST, but there are sort of 4 main programs that we really see within it. The main LSST survey is the Wide, Fast, Deep, which is designed to meet all the basic requirements, and this will take about 90% of the time. And this is the area that you see here in green. This is what we call the Wide, Fast, Deep survey. Then we also have deep drilling fields. We have 1, 2, 3, 4, 5. This is actually 2. This one's Euclid Deep Field South here. So we have these deep drilling fields, which we can go very deep to and have very short revisit times. In addition to that, there's a series of mini and micro surveys, for example, the North Ecliptic Spur, the South Celestial Pole, sorry. And then in addition to these 3, we will also operate in targeted opportunity mode. This is to reposition LSST in response to the observation of sudden transient phenomena, so for example, a kilonova event. Okay, now Micol will introduce the Euclid mission.
Thanks, Leanne. So Euclid shares a lot of science with LSST, and the main driver also is the cosmology. So the main question we want to answer with the Euclid is why the expansion of the universe is accelerating, and whether this is due to the so-called cosmological constant, or to a modification of the general relativity at the cosmological scales. And this can be achieved, this knowledge can be achieved by knowing the variables in the equation of state of dark energy, the W0 and the WA in that equation, to an accuracy of 1% for the W0 and at least 10% for WA. And this translates to a so-called figure of merit that should be larger than 400. And how to achieve this result is through different probes, different cosmological probes. The first one being the weak lensing, which is a study of the distribution of matter through the cosmic shear in tomographic beams. So to this aim, you need to have very reliable measurements of the shape of galaxies and reliable tomographic beams. So through photometric redshifts, And the other main probe is the peak of the baryonic acoustic oscillation, which is a standard ruler, and that can tell you about the calibration. It will constrain the distance redshift relation. And this is done through the study of clustering in 3Ds. And of course, to this, precise and accurate measurement of redshifts is needed. And another additional probe that will also be measured with the Euclid is the abundance of clusters that will measure the growth of the larger scale structure. So to realize all of these probes, we will need high quality imaging, and the photometric redshifts need to be computed with a high accuracy. And we will also need the spectroscopic redshifts, and all of this in a wide area, in a wide range of redshifts, with a larger sample, and of course with a perfect knowledge of all the systematics of this sample. The Euclid mission then will have two mode of observations, the photometric one, with the one broad optical filter, which is encompassing basically the RIZ filters that we all know, plus 3 filters in the near infrared that are used to complement the ground-based photometry to derive the photometric redshifts. Plus, for the spectroscopic part, we will need to observe many objects, and to observe to have a high density of spectroscopic redshift, we will need to have a slitless spectroscopy, again in the near infrared, because this range of a wavelength will probe galaxies in a redshift range where the cosmological leverage, let's say, is higher. So between redshift 1 and 2. And in fact, this leads to us to the definition of the survey of Euclid. There will be a wide survey that will observe most of the extragalactic sky in the north and in the south, because Euclid is a space telescope. So we can observe all the sky. That will be limited to in the optical to 24.5 at 10 sigma for extended sources, and in the near infrared to 24 at 5 sigma for point-like sources, and also with the spectroscopy, and aiming at observing the H alpha line in the redshift range between 0.9 and 1.8. This is also complemented by the deep survey that will observe 53 square degrees, much deeper than the wide survey, and it will observe 2 magnitudes deeper than the wide. And so the number of objects is huge. So yesterday we spoke about scalability. So it's really a problem, because the number of objects, as you well know, also for LSST, is enormous. So this is a mission that will take a 6-year time, and here in the plot you see how the observations will progress. So I think this is maybe for you. Yep.
Okay, so following that introduction to both missions, I'm sure that everyone can see that there's a lot of scope here for synergies between both of them. One of the key points to exploiting these synergies is to have a very large area of overlap. And from this map here, you can see, as Micol just explained, the Euclid sky map, and then this is overlaid in the green box here with the Rubin LSST sky area that I presented just earlier. So you can see that we have a very large area of overlap of 9,000 square degrees. In addition to this large area here, we also have 2 overlapping deep drilling fields, the EDF Fornax, which is 10 square degrees, and EDF South, which is 23 square degrees. EDF Fornax has been one of the LSST deep drilling fields now for quite some time. We have recently committed now for our 5th deep drilling field for that to be EDF South. So there's 2 areas of overlap here for deep drilling. In addition to this, there's an LSST cadence note. Many of you will know that the Survey Cadence Optimization Committee put out a call for cadence notes from the community to recommend changes. So tweaks, changes, modifications, additions to our baseline survey. One of these cadence notes recommended was it called Enhancing LSST Science with Euclid, and a mini survey of the northern sky to 30 degrees. This proposed modifications to our wide, fast, deep area, that's in this green part here, to have an extended footprint driven by dust extinction limits. And this will enhance this Euclid synergies and bring us up to 9,400 square degrees. So there's a very large area of overlap here, and that combined with the fact that the 2 missions are running roughly over the same time period, means that we have quite a lot of synergies here. This is a post on the LSST community forum, was put out by FED as a recommendation from the both following the derived data product working group report that I'll talk about in a minute, and the fact that the Survey Cadence Optimization Committee conducted an analysis of the Euclid Deep Field South. The SCOC has committed to, or has supports rather the selection of Euclid Deep Field South, and the project has now accepted this. So you can go to this post here for more details if you like. Okay, talk about the deep survey.
Yeah, and in Euclid we have 3 deep fields, 1 in the north and 2 in the south. The 2 in the south, as Leanne just said, overlap also with the footprint of LSST, of course. The first one is the Euclid deep field Fornax, which contains also the Chandra deep field south. So there are a lot of ancillary data that can be exploited in that region. And in Euclid, the deep fields are used to estimate the purity and completeness of the wide sample, but also they can also be used, of course, to explore deeper science on galaxy evolution and AGN and any other finding that can be achieved with deeper observations. But the other interesting field is the Euclid deep field south that Leanne just mentioned. It is very interesting because in that field we don't have any deep sky survey to date. So there is a huge room for discovery in that region. So it's really exciting to have both data from LSST and the Euclid together in that field.
Okay, so I'm going to talk to you a little bit now about the Rubin Euclid Derived Data Products Working Group. This was a group, was a community driven process that happened about a year or so ago now. We had about, sorry, wrong one. This here shows you the report. A large number of the community from both Rubin and Euclid came together and worked on proposing an initial set of derived data products that we could produce from both Rubin and Euclid data. We had about 350 people contribute ideas. This is the report. It was first released on the 21st of December, 21. We just put out a recent update with some minor modifications. You can see it's on the archive. You can cite it here. We have 120 authors in total. And I think one of the good things about this is that we have such a large author list. We had a lot of people contribute to this, and it shows that the recommendations in this report, the derived data products that we propose, have the support of the community. It's been a very inclusive process. It's not just someone coming along and saying, well, how about we do this? It was discussed at length by the wider community. We covered a large range of science areas from solar system, Milky Way, through to strong lensing, weak lensing, cosmology, galaxy clustering. We really feel that all the science that could be done, both Rubin and Euclid and with the synergies, is represented in this report, and they have proposed very specific derived data products that could be produced from the data products from a joint processing, but also from the data products produced individually by each of the surveys. We grouped our recommendations broadly into 2 categories. One is the cross-cutting DDPs and one is the science-specific DDPs. The cross-cutting DDPs were data products that we found would be useful to a very wide range of science. Photometric redshift, for example, was probably the biggest one that everyone would use and will benefit from both combining Rubin and Euclid data to improve our estimations there. And then in addition to these DDPs, that would, given the diversity and complexity of the suggestions there, we have 63 DDPs in total. Given the wide range and diversity and complexity of the suggestions, we recommended a tiered approach to implementing these. Some of these DDPs are really easy. You can see how to do them at the beginning of the survey. They don't require too much work. And others are much more complex, involve a joint pixel processing, and really won't benefit until when you have 2-3+ years of data from each of the surveys. So we also recommend a timeline and how you would go about producing these DDPs. This is just a first page of the report. You can see that the working group, we had, I think it's 13 members from Rubin, 13 members from Euclid. So it really was a community-wide, equally balanced between both projects' endeavor. In order to solicit input from the community easily, we set up a community-based forum. We did consider using Slack, but it was prohibitive in terms of cost and deployment. So we set up this community-based forum here, where anyone in Rubin or Euclid could create an account, come in, join, and express an opinion. And you can see that there were lots of really interesting discussions around a whole variety of topics: deblending, galaxy clusters, static cosmology, etc. This community forum is still there. Here is the URL. You can go and consult the discussions. You can add. I mean, people will still listen to it. We've put the report out now, so it's not so active, but we do have a whole history of the discussions here and how we produced the report. Okay, so I just want to step back and say, what is a derived data product? And we came up with this definition, which is in the report. Data are considered a Rubin-Euclid derived data product if the data product is derived from Rubin and Euclid proprietary data for the joint benefit of the two communities, while preserving aspects of each community's proprietary science. So neither Rubin nor Euclid have open data. And one of the concerns in this whole process was, how do we preserve our unique science? And so we came up with a way of defining DDPs, sharing data that wouldn't compromise each project's unique science. Of the 63 DDPs, you can see there's a whole wide range. I mean, I don't have time to go through every single one of them in detail, so I'm just going to present a highlight of what's in the report. But probably the most common one requested was multi-band Rubin Euclid deblended photometry catalog from joint pixel processing. This is quite a big task, and I'll show you in a minute. We recommend a ramp up to this and how we can start to achieve some of the benefits before we get into a joint pixel processing with deblended photometry. But this is a DDP that I think will be a broad benefit to all the sciences that I discussed between both projects. Photometric redshift distributions, so Rubin redshift distributions calibrated with Euclid spectroscopy. For solar system, there was an object light curve catalog, joint pixel star galaxy classification, dedicated low surface brightness pixel data reductions, a joint transient database and an interface to that, pixel level decomposition of quasars and their galaxies, and a joint color morphology catalog for strong lens searches. These are some of the highlights of what you can find in the report. If you're interested in these, I'd encourage you to read the report and come back with questions that you have about any of them. In addition to recommending derived data products, we also had some additional recommendations to optimize the joint scientific return. Some of them were around survey strategy optimization and joint simulation. So we've already presented how Rubin choosing the Euclid deep drilling field, Euclid EDF South, means that we now have 2 deep drilling fields in common across both of them. So we've tweaked, Rubin has tweaked somewhat its baseline survey strategy in order to optimize the synergies with Euclid. We propose a joint simulations project in advance of getting data to try to understand how to do the data processing and to try to quantify the return for some of these data products. Data access and joint analysis. I mean, how are we going to access this data? Where will it be co-located? Will it be co-located? How do we process it? How do we give access to the community? This is really important if you consider the size of the data sets of both LSST and Euclid. It's pretty unrealistic to think you'll just go and get a bit of Euclid data there and go and get a bit of LSST data there and download it and try to process it. So clearly we have to have a coordination around this joint processing if we're going to produce data that's useful to the community. Timescales and data releases, we want to try and sync things up so that we can optimize the DDPs. And then tooling, methodologies, development, and plus also with open data sharing, how do we share this equally between both projects? I think I've already mentioned this. We recommend a tiered approach to developing the DDPs, starting from simple catalog merging and cutout exchange to a full-blown joint pixel processing, including deblending. Okay, so here's, I mentioned that we had 5 cross-cutting DDPs. These are the 5, I'll just discuss these a little bit now. The first 4 are basically multi-band Rubin Euclid photometric catalog. This will be of use to pretty much every science. This T here gives it a ranking T1, T2, T3, this T0 for image cutouts. T0 is the easiest, that's a tier 0. We should start doing that immediately. T1 is the next one up to T3, which is probably better done once you have a couple of years of data. Plus, we also understand how to do these things. So these first 4 here, these will all improve the estimates of photometric redshifts, enhancing many areas of galactic and extragalactic science. We propose to start from a simple list-driven set of catalogs. So, for example, in Rubin and Euclid, if each project has a detection in its project, then it gets the data for that position, for that object from the other project to enhance its processing. So this is list-driven. We'd have some detections above 5 sigma in our bands, and we ask the other project. And then, oops, sorry. And then that's the simplest way to start. That's something that we can do very easily in the beginning with not a lot of effort. And then as we move through the surveys, this can then move to a joint pixel level processing based upon the lists obtained in the first one. And then later down, we can include deblended photometry catalogs as well, which is much more difficult to produce. The other one that was requested by pretty much all science was this one, an image cutout stamp delivery service. So for each survey, if you have a position that you can have an image cutout service from the other one to get just a small region of an image for your object in each survey. And this will especially enhance transient strong lensing and dropout science. So setting up an image cutout service, and this is something we think is probably one of the easiest things to do that we would do fairly early on in the process. I won't go through this. These are just the details of these. I've put these really in the slides for reference. It's basically what I've just said. This here explains our tiered prioritization. So here's the 5 cross-cutting DDPs again with the tiers. We rank them in terms of relative scientific priority. So what's the scientific interest? The urgency relates to the time scale on which it is needed. So if something is time sensitive, so small areas of a deep drilling field might be worth producing and sharing before you have a fuller analysis of a larger area. And this here is the cadence RT year data release. Real-time yearly data release is the cadence for producing the DDPs. So is this something we want to update on a nightly basis? Is this associated with transients? Is this something that will come out in a yearly release? Or is it something that will come out of a data release, which is not necessarily tied to a year? And so taking these three items into account, we came up with this tiered approach to suggest when we should produce these DDPs. So T0 is ready when both telescopes start to observe the same area of the sky. And this is obviously pertinent for image cutouts and a stamp delivery service. T1 is in conjunction with the LSST year 1 release expected currently for 2025. Tier 2 and 3 are in conjunction with the Euclid data release 2 and 3 respectively, which correspond to LSST year 3 and 4. And then T4 is pending definition of Euclid's current non-allocated time. So these are really illustrative DDPs, scientific ideas, but we really don't know when they would be good to do yet. Okay, so one of the most common derived data products to come out of this that crosses many sciences is photometric redshifts. So we thought that in this short session, it would be good to do a deep dive into how photometric redshifts can be improved with LSST, and Euclid and Micol will talk to you about that.
Thanks, Leanne. Yes, we decided not to go through all the science topics that could benefit from the synergy between Euclid and LSST. You can read them in the DDP document, of course. Photometric redshifts are fundamental for both collaborations. So I think all of you know what photometric redshifts are. They are a kind of very low resolution spectroscopy to derive the distance of galaxies. And they can be derived mainly with the two techniques, the template fitting and a more data-driven approach like machine learning or similar. And in the very past, they were dubbed a poor person redshift machine because they are less precise than spectroscopy. But lately, they have been considered as fundamental for many exagalactic surveys because you can derive the distance of galaxies for huge samples of galaxies at the same time. And photometry is cheaper than spectroscopy and can go deeper than spectroscopy. So they are really a fundamental ingredient of many surveys nowadays. And they enable a lot of science in Euclid and in LSST. The main driver, of course, of both surveys. They are fundamental to derive the tomographic beams for weak lensing and also to derive the clustering in the same beams in redshift. So this is also a constraint for cosmological models. And they can help to identify clusters of galaxies through the use of the full probability distribution function of photometric redshifts, but also they are used to explore and study galaxy and AGN evolution and their intrinsic properties, because finally the template fitting technique and also the machine learning technique are connected to the derivation of intrinsic properties of galaxies and AGN. To use photometric redshifts to derive the constraints on the cosmological models, both collaborations have fixed some requirement on their quality. They are pretty similar in Euclid and in LSST, as you see, in terms of the variance, or the number percentage of catastrophic outliers, and the bias, which is the difference between the true redshift and the estimated redshift in these tomographic beams. And so, as Leanne just said, there have been a lot of requested DDPs that deal with photometric redshifts, because the quality of photometric redshifts releases on the quality of photometry. So not only the coverage, the multi-wavelength coverage. So really it could be a benefit for both collaboration to have the full wavelength range span from U to H band, but also, of course, the blending that from space it's easier, from ground it's more difficult. So many of the DDPs were requesting not only the sharing of the catalog, but also the sharing of the pixel level to be able to deblend the sources. And here I will show you just how the combined data sets will improve the estimate of photometric redshifts for both surveys. Here are some plots that I did in the case of the different data releases of Euclid in the Southern Hemisphere. In the first data release, we will have access only to the DS data, so without the U-band, and a slightly less deep than LSST data. And you can see that going from left to right, as the time goes by, the quality of photometric rashes in Euclid will increase with the number of catastrophic outliers going decreasing a lot, and also the scatter will be very much improved at the end of the survey using LSST 4-year data. The same, you have the LSST collaboration published a paper on photometric rashes with the use of Euclid, and this is the Graham 2020 paper. And from here you see that using the LSST 10 years data, in this case, you can see that using only LSST as it is in the left, or adding the Euclid data up to 5 sigma or even up to 1 sigma can reduce the scatter between the true estimate and the photometric ratio to 1, and of course decrease the number of outliers. And this is especially true at ratios larger than 1, where, as I said, the information on cosmology is more important because the models start to differentiate more. So this is how the addition of Euclid can help also LSST to decrease the variance and to decrease the bias and the number of outliers. But we also have to know what the DDP doesn't include. In the first cross-cutting DDP, it is said that there will be no exchange of photometry between the two collaborations if Ri or Z or Y, J and H have a signal to noise from photometry smaller than 5. This means that in this example that I derived from a simulation, semi-analytic simulation, if I cut the sample, for instance, in H Euclid 24, at the time of the data release 2 of Euclid, we won't have ground-based photometry from LSST for 20–30% of our sample. And this is affecting mostly objects at ratio larger than 1, 1.5. So many interesting objects. And this is almost solved, but not completely, waiting for the data release 3 when we will match our Euclid observations with LSST 4 years observations. This was decided to somehow protect the science of both the collaborations, and also because these limits from Euclid and LSST were well matched to represent star-forming galaxies at a ratio around 1. So here in the rightmost in the plot, you can see that for a star-forming galaxy, the limits are quite are enough to detect a star-forming galaxy. But here I show you what happens if you want to observe a passive galaxy. In this case, you see the circles are the signal to noise 10 for all the LSST and the Euclid bands, and the small squares, the signal to noise 5. And the lines, the magenta and blue lines, represent the spectral energy distributions of a passive galaxy in magenta and a blue galaxy and a star-forming galaxy with the blue line at ratio 1.5. If the spectral energy distributions will fall below the squares, this means that the signal to noise is below 5. And this is the case when we want to exchange any photometry between Euclid and LSST. And this will happen also for the optical selection. but of course also for the near-infrared selection we will use in Euclid, but also for you if you select at I-25, also for star-forming galaxies. Again, this is almost solved, but not really for passive galaxies if we wait for the final Euclid data release. So this is showing you how the DDP is working, which is very good in many respects, but you also have to know what it doesn't contain. And this is just for Crescenzo, which is our chair, because Crescenzo is working in the local universe group. So this exchange also at the pixel level will be a real space of discovery for the low surface brightness galaxies, for which we will be able to perform a spatial resolved SED fitting and determine the properties of a galaxy. Again, spatially resolved. So this is something Crescenzo is working on. And I think this is for Leanne.
Okay, thank you, Micol, for that nice deep dive into the benefits of sharing data on photometric redshifts. So one of the other recommendations, a more general recommendation that we have in the report is to start a simulations project, a joint simulations project between the two projects to create realistic joint Rubin Euclid image simulation suite. Through discussions with many people while writing this report, everyone knew that there would be a benefit, and everyone had a sort of an idea of how much we would benefit by sharing data, but nobody had ever actually really quantified it, a lot of the things that they thought would benefit. So one of the proposals is to create a realistic set of image simulations to help quantify the expected gains from each of the DDPs that are proposed, but also and also not just to quantify the expected scientific gains, but to allow the development of DDP algorithms. I don't think that there's ever been an effort where we've done this sort of written algorithms to take data from each, different surveys with different detectors, with different cameras, with different PSFs, and to jointly process that. And so there'll be a lot of work in developing algorithms as well to do a joint processing of data. So we recommend starting up a joint survey working group around this. There are some efforts on this already. There's a NASA-funded effort to produce joint Rubin-Roman image simulations that we could learn a lot from. And there have been similar efforts by the Euclid Consortium. Micol will give us an example of this in just a second to build some simulations. That's for you, yeah.
Yeah, in fact, I think we are developing in parallel many things and also the simulations, as far as I heard yesterday from the desk collaboration. In Euclid, we are building the cosmological simulation, which is called the flagship. We had the flagship 1. We are using now the flagship 2, which is an improved version, and which is simulating the full sky, actually. But we are using 1 octant with a very good resolution, and we are going to start the simulation of the deep fields, more suitable for deep fields. This is the basis of simulations that will that are also treating that are simulating also images and having a full end-to-end simulation from the intrinsic properties from the cosmological simulation to the observed ones. So I think this is also one field where we can work together, probably as suggested by the DDP. And this is the timeline. This is what is written in the table by Phil Marshall, but take into account that actually both projects will start, I think, 9 months later than what is written there. So basically, the DDP can start as early as the first observations will be carried out for the transients, while in the black squares, especially after 2025, both collaborations will have access to full data releases that can be exchanged, and this will be the period where the science will be extracted. But of course, the calibration of all the pipelines should be done before. So maybe this is.
Okay, maybe in the interests of time, since I think Micol's just mostly said most of this, we're coming up against lunch now, and I'd like to leave some time for questions. I'll maybe just skip that. And that's, I think we've said most of this already, but this is really about the open sharing of the data across the Euclid Deep Field South. Maybe just one point is that we could observe the 2 Rubin deep drilling fields. It covers the Euclid Deep Field South is in fact 2 Rubin deep drilling fields. There is the option to observe both of them at half depth or a uniform depth with an optimal Rubin dithering. The feedback we've received is that covering the whole of the Euclid Deep Field South area at full area but lower depth is vastly favored by most of these cross-cutting DDPs for studies relating to galaxy properties and evolution. Okay, so I'm just going to try and wrap up here now and hopefully leave a bit of time for questions before lunch. We might be a bit late. Just to summarize where we are. So Rubin and Euclid have completed a community and science-based process to mutually identify derived data products that would be of benefit to both communities. The report was published, it's on the archive. This report describes all the data, the derived data products that the community could think of to exploit the synergies between both projects to maximize the return of both projects. We define cross-cutting DDPs that serve many scientific domains, for example, PhotoZ, joint photometric catalogs, and we recommend a tiered approach to implementation that reflects the importance and timing of each of the derived data products. Rubin has now committed to observing the Euclid Deep Field. Bob mentioned this in his talk this morning. All the EDF data from both missions will be shared simultaneously with both communities. This has no impact on the Rubin survey strategy. It has been recommended by the Rubin Science Advisory Committee, Rubin leadership, and the Euclid board has approved it. So this is great. We're going to move forwards with this. One point to mention, I think this question was asked this morning, is that everything we've described, all these data products, all this joint processing, none of it is funded at the moment. Neither Rubin nor Euclid had this as part of its scope when the proposals went in, when the project started. And it's not part of the Rubin operations plan. I think as Bob mentioned, we're quite pressed to execute our own plan in Rubin to get Rubin going. So we need to seek additional funding for this joint processing and to produce derived data products. We can't just ask the same people to do more work on top of what we're already asking them to do. As Bob mentioned again this morning, the next step now is a Rubin-Euclid joint letter of intent to move forwards with this that we can use to go to the agencies to try to push this effort forwards. And yeah, that's all we have. Thank you. Sorry, it's a bit late. We started a bit late, but we're happy to take questions now. Thank you.
So thanks, Micol and Leanne, for the nice talk. Yeah, time for question. Please, Simone. Yeah, there will be someone.
Hi, do you hear me with the microphone? Is it working? Okay, good. So I have 2 questions. One is very easy. So will the Euclid Deep Field South be prioritized in the cadence of the Rubin observations? So this is the first question. And the second question, being used to work with both ground-based and space data and used to combine them, I'm thinking to the depth of the Rubin observations, which will produce a lot of blended sources. So for the first, the T1, when we will just share catalogs, I'm wondering the percentage of the sources that will not be in that catalog matching just because they will be blended in Rubin. and also the colors of these sources that would be wrong because they're blended. So I'm wondering what this percentage of sources will be and which science cases will be impacted in a negative way by these incomplete catalogs, and which science case will be possible with these incomplete catalogs.
Okay. I have to admit, I found it a little hard to understand what you're saying with the mask on, so I'll try and answer it. I think your first question was would the Euclid Deep Field South observations be prioritized? I don't think we have an exact, I see Bob's at the back of the room, he might know better than me, but I don't think we have an exact schedule yet for when we're going to observe the deep drilling fields. But obviously we will think about this and take into account the synergies and plan accordingly is the best I think I can say at the moment. But we're very aware of the fact that we want this to be a successful project. So we will observe accordingly. And for the second one,
no, yes, it was the second question on the blending. I don't know, Simona, I think that in LSST, there is a huge percentage of the sources that will be blended. I don't remember exactly from the DDP, but it was something like 60%, huge. And yeah, and in Euclid, it is something like 10%. So
yeah,
yes, of course. Photometric ratios also will be crap.
Yeah, so I mean, you're right. Certainly, science cases are going to suffer because of this, and anything that uses the photometry or the photometric redshift. We propose just the very simple list-driven exchange of photometry at first, because that's an easy way to get started, and it doesn't threaten the unique science of each. But one of the DDPs was, as we move further through each of the missions and we understand the data better and we've got more experience with joint processing, that we would do a fully deblended, joint pixel level deblended analysis. But that's for the future.
No,
I'm sorry, could you take your mask off when
yeah,
you're
sure,
I
I'm
barely
happy to.
understood. I'm sorry, thank you.
I'm Adriano Fontana.
Yes.
And so I enjoyed being part of the working groups. Said that I completely disagree on this scheme that you set up, and this has been a lot of discussion, but that's what it is. My question is, what is the relationship between the process you described with the infrastructures that the two teams have already in place for dealing with the data? So in Euclid, we have a clear infrastructure in place to reduce data, to analyze the data, including data coming from ground-based images. And at the same time, you have certainly within LSST the capability to process the data, not the resources, but the capability, I'm saying, to reduce the data which may come from Euclid. So in this discussion, if I come from outside and listen to what you said, my impression is that, okay, they're starting from scratch again. There is no connection at all to the infrastructures and to the algorithms and to the processing that will be done in the two places. So my question is, what is the connection between this process you described and the standard analysis that will be done by the two teams? This is completely hidden, at least in the presentation.
So each project is going to obviously do its standard analysis of its data using the infrastructure that it has. We don't recommend just starting from scratch, obviously. There's a lot to be learned, but neither project is really resourced or funded to incorporate data from the other survey. And we have to look at how we put in place the infrastructure and develop the algorithms jointly to do this processing. But we recommended the scientific driven derived data products, and we also put in place a recommendation that said to look at the most efficient way to develop algorithms together, to look at ways in which algorithms could be developed, and we put infrastructure in place for this processing. But we don't have we didn't have a proposal specifically for how to do this, just that this needs to be investigated.
Yeah, my comment is, again, you described the intention essentially to restart from scratch. So as we are limited by resources, I find really surprising that you start with the most ambitious and undefined plan instead of doing what was practically doable with or with a small addition to the available resources. But that's a discussion we may have offline. So my question is specific. How are the two data processing units engaged in these exercise?
Sorry, I missed that. How is the?
So in Euclid, the ground processing is established, and in principle, they are prepared to include in the Euclid data processing the Rubin data. Okay, and I'm sure that on the other side, if your team has access to the images, they know very well what to do. So my question, and there is a plan. You have a plan to reduce the data daily. We heard today. Now you're going to reduce.
So are you asking if Rubin has a plan today to reduce?
No, I'm saying how you incorporate these, the analysis that you have described there, the T1, 2, 3, etc., in at least in a plan, in the data processing that you already have in place, or are you thinking about starting something completely independent from scratch that deals with the two data sets?
Rubin doesn't plan to incorporate this at this time in its processing. We will process the Rubin data just as it is, and we will put out Rubin catalogs and processed images and data products. We don't have a plan to do this. As I tried to explain at the end, this is increased scope. Neither project is scoped to do this, and we need to find more effort to do this, to think, well, how would we process this data together?
One thing I saw and another is what is it? Build something from scratch, or take these things and inserting that in the data process.
Okay, so I mean, I think that the exact way that it would happen is that the group of people who would be put in place to investigate this would almost certainly take advantage of what was already existing. I'm simply saying that in the Rubin standard processing, we're not including data from any other surveys. But if we want to go ahead with generating these derived data products, I'm fairly certain that the group of people who would be put in place to do this would take advantage of everything that's already been developed. Robert, did you want to add something?
Do you want to answer this question or different? Okay, so on the Euclid side, there's the OUX, right? And they are indeed processing ground-based data, but they're doing it then catalog matching. There's no concept of, that I know of especially handling the IR data and the ground-based data at the pixel level. On the, I think that's true on OUX. There's no one's driving the deblenders on ground-based. OUX is handling catalogs, merging at the catalog level. They're running consistent processing and then merging the catalogs. They're not injecting the, last I heard, okay, you can correct that in a moment.
No,
So,
well, sorry, Adriano can answer better than me, but OUX is reducing the data. OUMER is producing the catalogs in Euclid. They are not just merging.
yeah, but OUX is not taking the Euclid positions and reprocessing the pixel data with that information, as far as I know. Last time, you can tell me later. On the Rubin side, we're not, but we could. If we had the Euclid data, our data processing pipelines could perfectly well inject the different resolution data, handle the PSF matching. That's what our deblenders are handed to do. So if we were funded on our side, we could certainly do it. And you should tell me where I'm confused on the OUX, OUMER side on the Euclid side, to how ready you would be to handle the Euclid data. I know you're handling the SIMS.
I will go with the last question at the end of the room. If you can pass the microphone. Yeah, where is it?
We can discuss offline after that.
Okay.
Yeah, thanks.
Thank you for this roadmap and to the whole group for developing it. My question is basically about your last two bullet points. What happens next? How does this get funded and who gets to do it? Is this something that the agencies are planning to additionally fund the future Rubin operations team plus the Euclid team, or is this something that will be openly competed? Some of the things that you listed there, especially in tier 1, are things that groups with smaller groups with technology can do even outside these teams. So can you give us a sense more? Is this something that's more oriented towards the existing Euclid and Rubin team, or is there opportunity for the broader community to participate in an open call?
Yeah, thanks, Mario. So none of this is part of the current Rubin processing scope, and it's not part of the Rubin operations plan to do any of this work. We are putting together a letter of intent to try to put in place a memorandum of understanding with Euclid to use this to go to the agencies to get funding to do some of this work. Bob, do you want to answer?
Yeah, I guess my question is, how do you see this going, right? Not what's, I understand how the management works and what is there today, but is this moving in a direction where LSST and Euclid do it, or is this moving in a direction where it's an open call for the community?
Okay.
I think it's going to be somewhere in between. We haven't decided yet, but I think that the next step is for Rubin and Euclid leadership to put together a working group, not unlike what we did here with the science-based phase 1, to go to an implementation-based phase 2. And I think all options are open. We certainly, like Leanne said, Rubin operations isn't necessarily going to do this. There's natural ways where you could think, depending on how you did it, you would want that kind of scale. There's other places, like you said, where there's certainly places where people can contribute. And the main point is that these are two valuable science data sets that should be put together, not who gets to do it.
We need to understand that the opportunity exists.
That's right. And that will be coming out. We will do another, this phase the implementation phase will gather input and ideas from the community on how to make it happen.
Okay, just quick very final question.
Just to throw another spanner in the works, as part of LSST UK, I am developing more complicated list-based photometric catalog matching that can handle the deblending issue. If you'd like to hear more, I have a talk tomorrow in Stars Milky Way local volume.
Thank you.
On just T1 list-based matching.
All right, come along.
So thank you all for the questions. It is an interesting discussion. Of course, it is important to understand how the things will be done. And eventually you can discuss during the lunch. So I want to thank the two speakers. It was an exhaustive description of what is going on in the two surveys. And I also want to thank Vittorio and Vincenzo for the help. So enjoy the rest of the day.